Welcome to Podcast Learnin' Fun. Let's start today's journey of learning.
Today we're talking about magnetic dipole moments and spin angular momentum.
Ooh, those sound complicated.
They're fundamental to physics, though.
Okay.
And they help us understand how, the universe works at a tiny scale.
At a really tiny scale.
Yeah, like atoms and particles.
Okay, so first, could you explain what a magnetic dipole moment is?
So, think of it as a measure of how much magnetic oomph something has.
Magnetic oomph. Okay.
It describes the strength and direction.
Okay.
You can kind of picture it like a compass needle, always trying to align itself with a magnetic field.
Okay, so this applies to anything magnetic.
Anything magnetic, not just compasses.
Got it. Okay, so like the magnets on a refrigerator.
Exactly.
But what about the tiny particles? Do they have magnetic dipole moments too?
Yes, absolutely. And that's where things get really interesting. For example, electrons. They're not just tiny balls of charge, right? They also have this intrinsic property called spin. Imagine like a tiny spinning top.
Yeah.
And that spin creates its own little magnetic field.
Oh, wow.
The strength and direction of this field are all tied to the electron's spin angular momentum.
So it's like these tiny particles have their own built-in angular momentum.
Exactly. Spin is this purely quantum property. It's not something we can visualize in the classical sense, but it's just fundamental to how these particles are. And get this. Spin is quantized.
Quantized? What does that mean?
Meaning it can only take on certain specific values.
Okay.
Like think of it like a staircase where you can only step on certain steps. You can't just step anywhere in between.
So how do scientists describe or measure this spin if it's so abstract?
Well, we use this special number called the spin quantum number. It's denoted by the letters.
Okay.
For electrons, it's 1/2.
Okay.
Leading to two possible spin states, spin up and spin down.
So it's like flipping a coin.
Exactly, like flipping a coin.
Yeah.
You can only get heads or tails.
You can only get heads or tails,
Other particles have different spin quantum numbers.
Okay.
Like photons, the particles of light, they have a spin of 1.
Got it. So we have these particles with spin. Creating these tiny magnetic fields.
Yes.
How does this all tie back to the magnetic dipole moment?
So here's the key connection. A particle's magnetic moment is directly proportional to its spin angular momentum.
Okay.
So the faster it spins, the stronger its magnetic field. But there's a twist. The direction of the magnetic moment is actually opposite to the direction of the spin.
What? So if it's spinning up?
Yes. Imagine an electron with spin up. Its magnetic moment points down.
So it's like a flipped compass needle.
Exactly, like a tiny compass needle that's flipped upside down.
That's so strange.
It is.
Okay, so it's not just the strength of the field, it's also how it's oriented.
Exactly. It's all about the orientation.
And that orientation is tied to this quantum property of spin.
Spin, yes.
But what happens when you have multiple particles together? Like in an atom?
Right.
Doesn't it get more complicated?
It does. When you have a bunch of particles in a system, like an atom, their individual magnetic moments from both spin and orbital angular momentum all contribute to the total magnetic moment of the atom.
So orbital angular momentum, that comes from their movement, right?
Exactly. It comes from their movement around the nucleus.
Okay. So it's like
imagine you're trying to calculate the overall spin of a figure skater who's spinning and gliding across the ice at the same time. You have to consider both.
Both types of motion.
Yes.
So figuring out the total magnetic moment of an atom,
It is. It's a complex puzzle.
Yeah. Is there some kind of special factor that helps scientists make sense of all these contributions from individual particles?
That's where the Landé G factor comes in.
Okay.
It's a special factor that helps us calculate the total magnetic moment.
Okay.
It takes into account the interplay between both the spin and orbital contributions.
Of all the electrons.
Of all the electrons in an atom.
So it's like a mathematical tool.
Exactly.
It helps us untangle all the contributions.
All the contributions.
Of the individual particles.
Right.
And understand how their combined magnetic moments shape the behavior of the atom.
Exactly.
This Landé G factor, I'm guessing it plays a role in explaining.
Yes, it plays a crucial role.
How different materials behave in magnetic fields.
You got it. It's a key piece of the puzzle.
Okay.
But before we dive into that, Let's step back and talk more about the mathematical framework that scientists use to describe this peculiar property of spin.
Right.
It involves some fascinating concepts called Pauli matrices and commutation relations.
Okay, let's get into that.
Let's do it. It's just amazing how these kind of abstract concepts, these tiny particles spinning around, creating magnetic fields, it actually explains how magnets work in everyday life.
Yeah, that's what's so cool about this. Like, we all know some things are magnetic and some aren't.
Right.
Is that all because of how these magnetic moments of the atoms are arranged inside them?
You got it. It all comes down to how those tiny atomic magnets are arranged.
Okay.
Let's take iron, for example.
Okay.
It's ferromagnetic.
Ferromagnetic.
What makes iron magnetic is that the magnetic moments of all its atoms, they line up in the same direction.
So it's like a bunch of...
Yeah.
Yeah.
Like, imagine a bunch of tiny compass needles all pointing north.
Okay, and that creates a strong magnetic field.
Exactly, creating a strong overall magnetic field.
So that's why a bar magnet sticks to your fridge.
Exactly, all those atomic magnets working together.
Okay, but not everything's magnetic like iron.
Right.
So what's happening in those other materials?
Well, in some materials, like aluminum, the magnetic moments of the atoms, they're all jumbled up, pointing in random directions.
They cancel each other out.
They basically cancel each other out, so there's no overall magnetic field.
So there's no overall magnetic force.
Those are called paramagnetic materials.
Paramagnetic, okay.
They're only weakly magnetic if you apply an external field.
Okay, so it's kind of like...
Imagine, you
have a crowd of people.
Yes.
And they're all holding compasses. But each compass is pointing in a different direction.
Exactly.
So like east, west, north, south, and it all just cancels out.
That's a great way to visualize it.
Okay.
And then you have diamagnetic materials. Where the atomic magnetic moments, they actually oppose an applied magnetic field.
Okay.
They create a weak repulsive force.
Interesting. So they're kind of like...
They tend to be...
pushing back.
They push back against magnets,
Okay, so it's this kind of tug of war.
It's a tug of war.
Between the magnetic field and the magnetic moments of the atoms.
Exactly. Sometimes the applied field wins and aligns the moments.
And sometimes they resist.
And sometimes they resist.
It's just wild how these tiny...
It really is.
...atomic magnets create such different effects.
It's a testament to that interplay between spin,
Yeah.
orbital angular momentum, and quantization.
Quantization.
We've mentioned it a few times.
We have, yeah.
It's so central to understanding how this all works.
So you said spin is quantized.
Right.
Meaning you can only take on...
certain specific values.
Specific values, but...
it's not a continuous...
Yeah, I'm still trying to wrap my head around that.
Well, think of it like a digital clock.
Okay.
It can only display certain times.
Okay.
Like 1.00, 1.01, 1.02, right? It can't show 1.01 and a half.
Right, okay.
So in the quantum world,
yeah,
certain properties like energy and spin, they're like that.
So instead of this smooth continuous spectrum, it's just these... jumps between allowed states.
Jumps between allowed states, that's it. And that's what leads to all these unique properties, like the distinct energy levels in an atom, the way they emit and absorb light.
Yeah.
It's all because the energy is quantized.
Okay.
And then, of course, the magnetic behavior we've been talking about,
yeah,
that's tied to the quantization of spin.
So it really is all connected back to these...
it all goes back
quantum rules.
Quantum rules, exactly.
It's crazy to think how these tiny properties...
it is wild.
...on the atomic level can impact the whole world.
It really is. Everything from the colors we see to the magnets we use.
Yeah.
It's all quantum.
All right. So remember those Pauli matrices we talked about earlier?
Oh, yes. The Pauli matrices.
Can you remind me of what those are?
So they're a set of 3 matrices.
Okay.
And they're basically mathematical tools.
Okay.
That let us describe how spin behaves in 3 dimensions.
Okay. And you said they represent spin operators, but how do they actually help us?
Well, remember we talked about measuring spin along different axes?
Yes.
Well, these Pauli matrices, they represent the spin operator for each of those axes.
Oh, okay, like X, Y, and Z.
Exactly, X, Y, and Z. They give us a way to quantify the spin along each direction. And, because spin is a quantum property, it doesn't always behave how we'd expect.
Yeah, like you said, the order you measure things in can change the outcome.
Exactly. That's one of those quantum quirks.
That blew my mind a little bit.
I know, it's wild.
Yeah.
And the Pauli matrices help us capture that quirkiness mathematically.
Okay.
It's through these things called commutation relations.
Commutation relations.
Yeah, they basically tell us that the order you measure things in, it matters. It's a bit like if you turn left and then right, You end up in a different place than if you turn right and then left.
So it's like the quantum world has its own set of rules.
It does, has its own rules.
And these matrices are how we decipher them.
You got it. And understanding this language of spin is so important, especially for this field called spintronics.
Spintronics? What is that?
Spintronics is really cool. It's all about using the spin of electrons.
Okay.
Along with their charge.
Yeah.
To make new electronic devices.
So right now we mostly use the flow of electrons, right?
Right. Moving electrons around to create currents.
So Spintronics wants to use...
Spintronics wants to use the spin as well.
Okay. So instead of just the charge, are we talking about using spin up and spin down like zeros and one?
Exactly. You got it. It's like a whole new dimension for information.
Wow. So you're basically doubling the amount of information you can work with.
Exactly, doubling the information. That could lead to devices that are way smaller, faster, and more efficient.
Wow, so we could see things like crazy fast computers, super sensitive sensors that could pick up the tiniest magnetic changes.
Exactly, and that's just the start.
It's just crazy to think that this property of spin
it is amazing
could lead to all these advances.
It really highlights how important fundamental research is, Exploring these abstract ideas can lead to real-world breakthroughs.
This has been fascinating, but I got to say, my brain is getting a little full.
I hear you. We've covered a lot.
From tiny particles to futuristic technology.
It's been a journey.
It's just amazing to think about all this, These tiny particles with their spins and magnetic moments, they're like the building blocks of everything.
It really is. It shows you how connected everything in the universe is.
Yeah.
From the tiniest things to the biggest, the same laws of physics apply.
One of the things we keep coming back to is quantization.
Right.
I feel like that's super important here.
It is.
So could you remind us what that means again and why it's so important?
Sure. Quantization just means certain properties like energy, angular momentum, spin. They can only exist in specific values. So it's not like a smooth range of possibilities. It's more like steps on a staircase.
So not like a dimmer switch you can adjust gradually, but more like a light switch, on or off.
That's a great analogy. And that's what gives atoms their unique properties. And it explains how materials behave the way they do.
Okay.
Like the fact that atoms have these distinct energy levels. That's a direct result of quantization. And of course, the magnetic behavior we've been talking about, well, that's because spin and orbital angular momentum are quantized too.
So this idea of quantization, it really does have this huge impact on the world, even though it's kind of abstract.
Absolutely. It's a fundamental part of how the universe works. It's at the heart of quantum mechanics, the theory that governs the tiniest stuff.
And, we've talked about how Spintronics wants to use the spin of electrons along with their charge.
Right.
What are some of the ways we could actually use this technology?
Oh, the possibilities are huge.
Yeah, you mentioned faster computers and really sensitive sensors.
Those are just a couple of examples. We could see super fast, super efficient computers. We could have incredibly sensitive medical imaging devices.
Wow.
And maybe even new kinds of solar cells that use the power of electron spin.
That would be amazing.
And who knows what other incredible applications will emerge as we learn more. That's what's so cool about basic research.
Yeah.
Sometimes exploring these abstract ideas can lead to breakthroughs that change the world.
It's pretty inspiring to think about what we might be able to do with this.
It really is. And it all goes back to understanding these fundamental concepts: magnetic dipole moments, spin angular momentum, and the power of quantum mechanics. It shows you that the pursuit of knowledge, even in the most abstract areas, can benefit all of humanity.
I think we've covered a lot today. We've gone from these tiny spinning particles to these big ideas about future technology.
We have. It's been quite a journey.
Thank you for listening to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.